Thanks for coming, thanks for the invitation. It's been an enjoyable program. So I'll be talking about something very different from the other two talks today. Now we're moving into tidal flows in giant planets. And this is work primarily done by Christina Pontin, who's an SDFC funded PhD student in Leeds with myself and Raina. She finished about 2 years ago, and we've finally written up all the work from her thesis. And I'll be talking about that this morning. So quite different from what I talked about at the KITP layering program 3 years ago over Zoom, where I talked about a different aspect where layering can come into astrophysical fluids. So this problem is looking at gravitational tidal flows in planets deformed by their moons primarily. And we've got a highly exaggerated image to illustrate the picture on the right. So I've got Jupiter and Jupiter's moon Io. Jupiter's deformed both by its own rotation, which is what you might think you're seeing mainly. That's not what I meant to show in this figure, but actually that is probably the larger deformation. There's also the gravitational tidal deformation of Jupiter due to its moons. That is actually really small. So if you calculate the radial displacement of the equilibrium tide in Jupiter or Saturn due to their largest moons, it's of order 10 to the minus 7 or something like that, relative to the radius of the body. So these planets are very weakly tidally deformed. So this is a highly exaggerated image. And we know about tides in the Earth moon system, so the barotropic or equilibrium tide in the Earth's oceans, which gives approximately 2 high tides and 2 low tides in a day. So we also have an equilibrium tide we expect in giant planets. And also, like in the Earth-Moon system, there's also a wave-like tide on top of that, and that's primarily responsible for the dissipation. And that's what I'll be talking about today. So in the Earth-Moon system, we know that the moon's moving away from us at a few centimeters per year, and the Earth is gradually spinning slower and slower at a few milliseconds per century. Similar processes can occur in planet-star systems and also in planet-moon systems. And we have observations of the moons of Jupiter and Saturn that indicate that the moons are gradually, in most cases, moving away from the planet. So we're in a similar tidal region in parameter space in that sense to the Earth-Moon system, in that the Earth rotates faster than the moon goes around us. That's also true of these planets rotating faster than the moons go around them. So the tidal dissipation inside the planets tend to drive the moons to go outward. And so I'm going to focus on looking at the fluid dynamical mechanisms responsible for this in some idealized theoretical models to look at how rapidly tidal evolution proceeds. So for both Jupiter and for Saturn, we have observations, very detailed observations over the past just over a century or so, astrometric observations of the moons of Saturn and of Jupiter, including recent ones from Cassini and I guess Juno, but also older ones from telescopes from more than a century. And these we can interpret in using a very complicated model, taking into account general relativistic effects, perturbations, gravitational perturbations with the rings of Saturn, and oblateness of Saturn, and lots of complicated effects. But what we can get from these models is we can constrain the efficiency of dissipation inside Saturn and inside Jupiter in the Jupiter system. And this is just a figure showing some constraints we have of Saturn's, essentially how efficient tidal dissipation is in Saturn at the frequencies of these moons. So it's tidal frequency along the x-axis, corresponding with various moons, Enceladus and Futuria. And the y-axis here is essentially, well, K2 over Q, which is a measure of the dissipation. So the larger value that is, the more efficient the dissipation is in Saturn. And we usually, well, one way of quantifying the efficiency of the dissipation is in terms of a tidal quality factor, which to within order 1, possibly even one order of magnitude factors, is essentially a fractional tidal energy dissipated in each tidal period. And the observations tell us that we need a tidal quality factor of about 10 to the 3, very approximately, to explain the observations. There are some theoretical ideas for this that have been proposed, some more plausible than others, and I'll be talking about scenarios that involve excitation of gravito-inertial waves and inertial waves in Saturn to explain this. So there are similar observations for Jupiter as well, but I'll primarily focus on Saturn because we have stronger observations of the constraints on the properties of stable layers in the interior of the planet, which can be important for this problem. So Saturn, because of its rings, is we have another way of probing the interior of the planet through looking at oscillation modes in the rings. So we can look at features in the rings and look at where they occur in the rings and the associated frequencies that would be excited if you observe certain features in the rings. And they can be associated with resonances with internal oscillation modes in Saturn and the associated gravitational potential perturbations due to those. So this is a unique way of looking into the interior of a giant planet in the solar system enabled by the presence of the rings. And this was proposed in the 1980s, and some theoretical work has been done in the 1990s, but it's not really until the past decade or so that these constraints on the particular frequencies of these ring oscillation modes have indicated that it's highly likely that there's a stably stratified layer in the interior of Saturn. And the observations from Mankiewicz and Fuller, which I've indicated up here, indicate, well, there's a density profile as a function of radius in Saturn. There's also the buoyancy frequency profile in units of the dynamical frequency, which is the square root of gm over r cubed in Saturn. And in their models, to explain these ring oscillation modes, they need a stably stratified core out to about, well, 60%, possibly even more of the radius that's quite strongly stably stratified, with buoyancy frequencies comparable with the dynamical frequency. This is very different from classical pictures of giant planet interiors where we might have a solid core in the interior, well, more or less, with a neutrally stratified convective envelope. This is a very different picture to that, and it's a more recent picture. And I don't think the implications of this have been fully understood. So I'm going to focus on the importance of this stably stratified layer for the tidal response, which hasn't been that well explored. So aspects that I won't touch upon, but are also important here, is that the Prandtl number in giant planets is small. So thermal diffusion is much more rapid than viscous momentum diffusion, and also than diffusion of composition. So it's possible in this regime, because we have stabilizing compositional gradients due to heavy element gradients in the interior, that we could have instability to oscillatory double diffuser convection, either in the past or possibly currently, although there's lots of uncertainties about that. And whether or not that's linearly unstable, it's possible that there could be layering due to double diffuser convection and the presence of density staircases in the interior. We don't have any constraints, certainly observationally, on that. The constraints just tell us more about the overall buoyancy frequency profile. But these are interesting theoretical questions. And whether, if we do have a solid core at the interior, whether it can persist or whether it's eroded by the fluid motions. And that's without even discussing magnetic fields. So the impact of this stable layer on the degeneration of Saturn's magnetic field, the dynamo problem, hasn't been fully appreciated. So there's lots of unsolved problems here, but I'm only going to focus on the tidal response and in looking at the effects of the stable layer on that. So when we're looking at the tidal response in a planet or a star, primarily fluid body, well, similar picture really for the Earth, we can split the tidal response into two components. So one of them is the large-scale equilibrium tide, which is like the barotropic tide in the Earth's oceans. This is quite small amplitude in these planets due to their moons. So the tidal deformations of Saturn and Jupiter due to their largest moons, as I mentioned, they're about 10 to the minus 7. So the radial displacements are tiny in these bodies due to their moons. And so to a first approximation, at least when we're looking at large-scale tidal flows, we might think we can neglect nonlinear effects. So that linear tidal theory is valid. And whether or not that's true for the waves is a separate question, but for the large-scale tidal flow, I think that's reasonable. And so effects like the elliptical and precessional instabilities and other things that require large deformations are probably not in operation, or at least important. So it's been thought that the equilibrium tide can be damped through its interaction with turbulent convection. And the idea is that turbulent convection can act as an effective viscosity that can damp this flow. This is also thought to be quite weak because convection is slow in giant planets relative to the tidal periods. So this is thought to be ineffective. On the other hand, the dominant mechanism, in some ways like tides in the Earth's oceans, is likely to be the wave-like or dynamical tide. And we can either have gravito-inertial waves in stably stratified layers or inertial waves in neutrally stratified convective regions where the stratification is close to being neutral. And in fact, what I'll talk about is both of these, although the dominant one is actually the inertial waves, as I'll illustrate. So our model is going to be very simplified. It's going to be a Boson-esque spherical planet that's initially uniformly rotating and unmagnetized. And we're going to adopt a fixed gravitational potential for the body. So we're not looking at the resonances with ring oscillation modes and the real part of the love number. What we're interested in here is the dissipation. And so we're going to neglect self-gravity, because in the context of a Boson-esque model, including self-gravity is not that challenging to do, but I think it's in some ways more artificial to do that than if you were to have a realistic body and do that. So it's about the simplest model you can have, looking at tidal flows in a model of a giant planet. But there are aspects of this model that have not been well explored previously. So we've got a Boson-esque, tidally forced Boson-esque spherical planet. So we've got a tidal potential in here, and we're going to force the tidal flow with the tidal potential and with the fact that we've got a free surface at the top. We're going to have a lower boundary in these, which is in most cases not, at least when we have stable layers, not typically important, but we're going to have a stress-free impenetrable boundary at the bottom. For the buoyancy variable or density field, it's not entirely clear what boundary conditions we should have, but luckily the results are not strongly sensitive to that, unless you choose something which is inconsistent with the tidal flow. And so what we're doing is a combination of an analytical and numerical study looking at this system. But when you add the Coriolis acceleration in here in a spherical shell geometry, this becomes quite a complicated problem, and we need numerical calculations to explore many aspects of this. And we're using spectral methods, so Chebyshev collocation in radius and vector spherical harmonics in latitude. And the key aspect of this model is the buoyancy frequency and its profile with radius. And we're going to impose various different profiles of that with radius. We do also vary the gravitational acceleration as a function of radius, from being either linear with radius, as you might have in a homogeneous body, or 1 over r squared, as you might have in a centrally condensed body. But for our purposes, it doesn't really change things that much. The main thing that plays a role here is the buoyancy frequency profile. And for harmonic responses, which is what we're going to be looking for, we're going to just look at the response of the dominant tidal component, which is quadrupolar with m is 2. And we're going to look at the linear tidal response to that component. So we know that component needs to satisfy energy balance. So we need the energy that's input by the tidal potential is going to be balanced by a combination of viscous and thermal diffusion in this model. And there are a number of dimensionless parameters. We're going to use the dynamical frequency, which is essentially the frequency of the lowest, largest wavelength surface gravity modes as the typical time scale, and the outer radius is a typical length scale. And there are a number of dimensionless parameters in the system. The rotation rate is one key one. The buoyancy frequency profile and magnitude is another one. We also have something that's essentially an Ekman number in here, and Prandtl number, and we've varied a range of these. But the key one is the stable layer. So we had these constraints from Saturn, and we can try and use models that match that. But more generally than that, we don't know what it's not well constrained. So essentially, whether it's something that is has a uniform n and then drops off at 60% of the radius, or whether it varies within that, whether it even has a staircase profile is not well understood. And in older models of Saturn's interior, it's been proposed that could be a stable layer that is near the hydrogen-helium rain region, which could be like an interface, a stably stratified interface further out, or localized spike in n squared. So that we can also explore in the context of these models as well. And I'll be discussing these in the context of a solid core which has a radius of alpha, but this is really just used as a lower boundary condition. Unless we don't have a stable layer, it's not terribly important. Beta is going to be essentially the outer radius, fractional radius of the stable layer that we have in this model. So what are the results from this? Just showing some examples. So the tidal response is very frequency dependent. So this is showing a frequency in units of the dynamical frequency and dissipation on the y-axis, split up into its different components in cases where there isn't just one. So on the left, I'm showing an unstratified neutral convective envelope with a large solid core. So this is as if there is a solid core that goes out to 50% of the radius. Just for illustration, And in this model, the only waves in the system are the surface gravity modes at the right, essentially, modified by rotation. We can more or less understand these analytically. And on the left, there's inertial waves that exist below the Coriolis frequency, 2 omega. And there's a large range of these inertial modes that fill up this region in frequency space. And most of the peaks that we're getting in the dissipation correspond with the least damped eigenmodes. So the squares are showing the results of eigenvalue calculations. The y-axis for those is the damping rate of the modes. So the strongest peaks here are typically corresponding with the least damped eigenmodes. And what these are on the left is inertial modes in the convective envelope. And on the right, what I'm showing is a model that has a tiny solid core in the interior, which is not terribly important, but it has a stable layer that is uniformly stratified with a buoyancy frequency of 1 out to about 50% of the radius. And so it's essentially just a stratified version of what's on the left. So it's a fluid layer with a kind of extended core that goes to half of the radius. We also have surface gravity modes at the right, although these are normally outside the range in which we expect to excite outside the range of tidal forcing for the moons. But inside here, we now have gravito-inertial modes in the stable layer, but also inertial modes in the envelope. And you can see that the features on the whole are actually quite similar between these two cases. This isn't as obvious here as it is in this example. So what I'm doing here is showing 4 different models that model the stable layer in different ways. One of them doesn't have a stable layer. It has a solid core that extends to half of the radius, which is in blue. The one that's in the reddy color, that one has a uniformly stratified stable layer at 50% of the radius, and then a convective, neutrally stratified envelope outside of that. The yellow one has a single stably stratified interface with the same mean buoyancy frequency at that same location, so 50% of the radius. And the one at the bottom right, you can maybe just see in this image of one of the 4 solutions, it actually has a staircase with 3 steps in it in the interior region here, with a buoyancy frequency that's the same as the other 2 models that are stably stratified. So qualitatively, if you look at the plots on the right, which correspond with a frequency of 0.2 in dimensionless frequency of that, in the convective envelope, the response is quite similar. So it's not the same in each case. There's slight differences in amplitude, but it's overall quite similar. Whereas the response in the stable layer can be very different between these. But if you look at the dissipation, in the low frequency regime, essentially, they all behave very similarly. So the individual resonant peaks and troughs are shifted around by the properties of the stable layer and its size, but the typical properties of this model are the overall dissipation in this model is quite insensitive to how you model this stable layer, if the stable layer is sufficiently strongly stratified, and this value is not too far off the value for Saturn. So the primary effect here is actually, at these low frequencies, inertial waves in the envelope that dominate the tidal response, and not gravito-inertial waves in the core. I'll come back to this possibly. So in relation to the observations, we've got a very simplified model of Saturn. So it's a Boussinesq model with modeling the stable layer in a variety of different ways. But if we have a stable layer that goes out to Saturn's 60% of Saturn's radius with a buoyancy frequency of 2, and we use a rotation rate that's consistent approximately with that of Saturn in units of the dynamical frequency, then we do get values of the tidal quality factor that are consistent with observations. So broadly along the lines of 10 to the 3 within the range of Saturn's moons. So I've indicated those frequencies in here. Note that they're negative just due to how we've defined the tidal frequency. So despite the simplicity of the model, we do get values that are consistent with those of the moons. I'm not claiming that, because I think these values are going to be very sensitive to details in the model, the individual peaks and troughs, but the typical magnitude in the range in which the Saturn's moons force Saturn are roughly matched. But the details do depend on how exactly you model the stable layer, but the typical level of dissipation in this range is relatively insensitive to that. So this is showing you dissipation now is a function of frequency, so it was actually the same as the previous plot, but essentially 1 over it for one of the models. And I'm plotting 4 different models on here, and you can see that they're all broadly similar, similar levels of dissipation within the range of Saturn's moons. So you can view that as either positive or negative. Positive in the sense that if you have a stable layer that goes out to about 60% of the radius, it isn't that difficult to get typical values of dissipation consistent with observations, but negative in that we can't use these observations of the migration rate of the moons to constrain the details of this stratified layer. So we've also done some exploration looking at, well, wave propagation and the forcing of waves in a staircase, so whether we're obviously limited in these sorts of calculations which involve large matrices in terms of the types of models that we can explore. We can't explore 1,000 steps, but we can look at how sensitive the results are to the number of steps. So essentially what we're doing is now we're fixing the mean buoyancy frequency to be 1, and we're just varying the number of interfaces, the number of steps that we have within a staircase. And broadly what happens is you increase the number of steps, it does approach the properties of a uniformly stratified medium, so continuously stratified medium, as you might expect. But the resonance locations in frequency and the particular resonant peaks and troughs do depend on exactly how you model the stable layer. But the typical level of dissipation does tend to converge to something which is quite insensitive to the number of steps. So in the interest of time, I'll wrap up. So I've discussed how tidal dissipation in giant planet systems can drive the orbital migration of the moons. So in Jupiter and Saturn, we have strong constraints on those. We have constraints in Saturn of an extended, stably stratified layer in the interior due to ring seismology. And recently there have been a number of groups looking at exploring the effects of stable layers on the tidal responses, and found these to be very important for the tidal responses. So similar pictures very broadly found for the tidal response in Jupiter, and stable layers are likely to play an important role in explaining the observed migration rates of Saturn's moons. So this model, as I mentioned, is extremely simplified. And there are a number of effects that we could do to extend it. So compressibility doesn't change things too much. So if you have density variation in here, that doesn't change things massively. Effects that haven't been well explored in the context of this model are magnetism, double diffusion, which is only starting to be explored, and the more fundamental question really is how are these inertial waves dissipated ultimately? Because we know that we think it's unlikely to be dissipated by viscosity, microscopic fluid viscosity. So we're assuming that its interaction with turbulent convection, does that act like a turbulent viscosity or not? There are open questions that we really need simulations to probe, and they're things I'm interested in looking at. So I think I'll stop there and point you to these papers and Christina's thesis, which is online. So thanks for listening.
Thank you very much, Adrian. I'm actually going to jump in with a question because what you talked about is of interest to me. When you have uniform stratification, of course, you get the attractor structure for internal waves.
You mean the envelope or the whole region?
Pictures like that out there. But then when you put in a staircase, I'm wondering how much that disrupts the attractor. Because now you're going to get internal reflections from each of these steps that might get rid of that geometric structure.
Yeah. So yeah, it depends on exactly. So in the model at the top left, for example, there's a single stable layer, an interface essentially that's halfway halfway from the center, and outside it's just neutrally stratified, and that's purely inertial waves. And you can see the typical orientations of those and those sort of structures. It's definitely true that what you get there is changed by, if you add in more steps than you're seeing here, for example. It doesn't look very well. It is spatially resolved in the calculations, but you can see here it doesn't look very nice. You can see there are reflections at the interfaces of the waves, and you get something which, well, it's a global mode here. It's not something where we're forcing, it's not an initial value problem where we're actually looking at the resonances. But yeah, the structure of them is changed by the number of interfaces that we have. And yeah, it depends on whether we're in a stratified layer or... So here it's just the mean stratification that we're fixing. So it's neutrally stratified in between the interfaces, so it's essentially inertial waves. But then the interfaces are clearly playing a role in the existence of these modes. I'm not sure, I don't think that answered your question. Sorry, what was the... I think, yeah, interesting question. I'd like to understand more about the properties of these modes.
Yeah, so the dissipation is a global estimate.
Yeah.
And so if you look at it locally, say for in the structure of the beams, do you see regions where the dissipation is enhanced?
Yeah, so in fact, so I'm plotting here the magnitude of the velocity, but if you were to plot viscous dissipation, more or less it tends to align with the features that we're seeing here. So it corresponds really with where the solution has larger amplitudes. The dissipation is very strongly correlated with these.
One feature
So it's very spatially localized in the regions where the modes are.
Yeah. One feature that caught my eye is that where you see the beams graze the interior core,
yeah,
it lights up, and
that's
that
right.
seems consistent with critical reflection.
Yeah, that's right. Yeah, so
spots of dissipation.
It's likely that the critical latitude on an inner core, or indeed in a stably stratified layer such as the interface, well, an interface that we've got here, is very important for the response in the envelope. And there are lots of things that are not well understood about this, but we can review many aspects of this problem by thinking of, well, one way of viewing this problem that's been used in the past, there's a nice paper by Goodman and Lackner that used a way of trying to interpret what's happening in the envelope by thinking about the scattering of the equilibrium tide from the critical latitudes on the core, and that being a way of exciting inertial waves in the envelope. So while there are lots of aspects of that that are uncertain, I think the idea that something that's definitely true in these false calculations is that the waves are, it looks like these waves are launched from the critical latitudes on the core and then bounce around, and that's what sets up the response. So they play a huge role in this. The critical latitude singularity is important for these.
We'll take one more question from Gordon at the back.
What would you say are the prospects for resonant locking as is being proposed for migration, well, particularly Saturn's moons, especially the outer ones like Titan?
Yeah, good question. So we haven't directly looked at resonance locking. I think it's an interesting idea, and it could, well, the resonance locking idea is one way of, for example, explaining why you might have is it rear or Titan? Yeah, so the resonance locking ideas have been proposed to explain the variation in Q in Saturn. So I think so essentially what that is where as the system evolves, you can remain locked in one of the resonant peaks so you can remain in a circumstance where the planetary oscillation modes, frequencies of those are evolving at a similar timescale to the orbit, and then you can remain locked in one of these peaks. So I think that's an interesting idea. I've always been a bit skeptical about that because I've never been sure how robust those resonance locks are when you include other effects like differential rotation, the interaction with convection. So I think my answer to that is I'm not sure, but I think the idea of resonance locking has been an interesting one to look at. But I've always been a little bit skeptical, but it is a way that produces very nice, simple results that can be compared with observations. That, yeah, I definitely think it's a nice thing worth studying.
We have a final
I don't think that actually answers the question fully.
Yeah, I thought this idea that that the structure of the rings could tell us something about the interior structure was really interesting. And presumably there's a lot of mass in the rings. To what extent would you need a model that also has the rings in it, as well as a model of the planets?
In terms of the tidal response, how that would affect anything, or
like how might they feed back on each other?
So I think the rings are relatively, well, very low mass relative to Saturn. So
Okay.
Saturn's really massive.
Yeah.
So that impact on, at least on the tidal response, I think is probably not important.
Okay.
It's more the interaction of the internal oscillation modes, the fact that they can do anything that's observable in the rings is the key aspect really. So I think the rings are very low mass.
Okay.
Okay, so let's thank Adrian once again.